Hey, thanks for joining me. In this recording, we're going to cover continuous random variables. This is lesson 1.07. And we have some goals. The goals are to recognize the difference between uniform and non-uniform probability distributions. So we're going to see both, and we're going to try to figure out how to calculate probabilities of both types of probability distributions. And all of these are going to be continuous random variables. Continuous. So we're going to talk about that definition first before we jump into what on earth do we mean by uniform and non-uniform. Okay. So what is a continuous random variable? To explain that, I want to talk to you about another kind of variable, a discrete variable. So I have chickens and they lay eggs. So as you think about chickens, one of the pieces of data that we can count with chickens is egg production. How many eggs do they lay each day? I've got about a dozen chickens. They lay about 10 eggs a day. But think about the number of eggs they lay each day. It's possible that some days we're going to get 10 eggs. Some days we might get 12. We might get, on an off day, we might get 8 or 6 or 7, 11, 9. But, and we could chart this, like how many days did we get 10 eggs, and how many days did we get 11, and how many days did we get 12, and so on and so forth. And that would be a histogram. We can graph the data in a histogram, a bar graph. But think about this. The reason we can do that is because did we ever have a day where we got 8.5 eggs? Did I ever have a day where I had 8.5 eggs laid that day? And of course, that's a ridiculous question. The answer is no. That it never happens that your chickens lay 8.5 eggs. They only lay whole eggs, and so we can count. We can measure our data based on how many eggs each day, and in whole units, so whole numbers of eggs. That is called discrete data, a discrete variable. When we're talking about whole amounts of things. Now that's going to be useful for us if we're counting people, right? You can't have 3.5 people. They used to make all kinds of jokes about the average family number of children in a family was 2.5 when I was a kid. When you're counting things that can't be cut up into pieces, that can't be measured in pieces, that have to be measured in whole units, that's what we're going to do. And that's mostly what we've done so far in this class. But there are other kinds of data that we can measure that are what we call continuous. So just to keep with the chicken theme, how about if I take my eggs and I weigh them? So if I weigh my eggs, what different weights could I get? Well, it turns out that the average egg weighs about 2 ounces. Although you can get eggs that weigh up 3 ounces and even 4 ounces. And I actually have some chickens that are kind of small that give me eggs that might be closer to 1 ounce. But is it possible for me to get an egg that's 1.5 ounces? And the answer is sure, absolutely. You can get an egg that's 1.5 ounces. You can get an egg that's 1.9 ounces, or 2.7 ounces, or 2.98 ounces. There's lots of different weights of eggs that I could get. So I wouldn't really be able to do a histogram with a bar graph because we'd have all these just bunches and bunches of little bars for all the different weights. It just wouldn't make sense. And so in that case, I'm not going to do a bar graph. I'm going to do a line graph. that's how I'm going to measure my data. So that's what we're talking about when we talk about a continuous random variable. It's where we can't break up the data into whole numbers. There's too many small pieces that we're measuring there. Okay, that was a long explanation for just the use of the word continuous variable. And now we're going to move on to actually doing stuff. Okay, we looked before about probability distributions, and if you remember in the past, the probability distributions were represented in graphic form as a histogram, so we had that bar chart. And if you added up all the probabilities, the probability for each bar, they all added up to 100%. Well, now we have a continuous variable that we're talking about. In this case, it's wait times at the doctor's office. You could wait for 5 minutes before you see the doctor, or you could wait for 10, but you could also wait for 11 or 12.5 minutes or 13.2 minutes. So it's a continuous variable, so we can't just have discrete percentages, but we can see that there's this trend in percentages. So the probabilities go up, the probability of waiting, so that the highest probability is for 20 minutes, 20-minute wait time is the most likely wait time. And then for longer and longer wait times, the probabilities go back down again. Okay, so remember how those probabilities all had to add up to 100%? It turns out that these probabilities do add up to 100%, but how are you going to add them? How are you going to add the probability for 10 and 15 and 20, but also for 11 and 12 and 13-minute wait times? Well, the way that we're going to, I'm just going to tell you, this is getting dangerously close to calculus. The way that we're going to measure that is we're going to say that the area under in the graph, the area of that triangle, is going to represent the total probabilities, the total probability all added up. So when I add up the area of that triangle, I get my probabilities, and the area of any piece of the triangle is the probabilities for the wait times covered by that piece. So I can chop this triangle up into pieces, and the area within each piece is the probability of the wait times marked off there in that area. Okay, so before we go into specific questions here, let me just demonstrate how you find the area of a triangle. Remember, the area of a triangle is 1/2 base times height. 1/2 times base times height. And in our big triangle, that whole thing, the entire probability distribution that should add up to 100% or 1, the base is the length from 5 to 30, the number of spaces from 5 to 30, which is, just to get that, you just do 30 minus 5. So B equals 30 minus 5, which is 25. And then the height is the tallest tip-top point of the triangle there. That's how high it is, and that on our chart is 0.8, or 0.08, sorry, got that wrong. Okay, now here's the deal. I can do this on my calculator, and you can trust me, but it'd be better if you did it on your calculator, so hit pause and try this on your calculator. Well, it's 1/2, 0.5 times 25 times 0.08, and what do you get? And if you did it right, you should get 1, which is 100%. So the area under the triangle is 100%. Hooray! That's what it was supposed to be, and that's what it is. Congratulations. Okay, so what about a question? We haven't really asked any questions here, so let's ask a question. And I actually didn't have one, so I'll just make one up. What is the probability that you have to wait more than, let's say 25 minutes. What's the probability you're going to have to wait more than 25 minutes? Now, that question, the answer to that question, and the way that these are going to work is the answer to that question is the area of the triangle that's the section of this big triangle from 25 on over. Okay, so that whole section right there. Okay, now this is a little bit tricky. We have to figure out where this 25 line hits this line of the triangle there. And I want to say that that's, I'm going to go ahead and say that that is at the 0.04 mark. So that goes to 0.04. Okay, so the area of this little triangle here is going to be 1/2 times the base. The base goes from 25 to 30. That's the longest wait time. It's 25 to 30, that's 5. So 1/2 times 5 times the height, which is 0.04. And we multiply that together, and I think that comes out to be 0.1. Yeah, 0.1, which is equal to 10%. So there is a 10% chance that you're going to have to wait longer than 25 minutes at this particular doctor's office, which is pretty good. All right, so let's just run through a few more examples so you kind of see this. We're going to do a bunch of examples, so I'm going to try to go a little faster. Here is one where we have, this one is a little bit different. I want to talk about this one. The real numbers in a data set are distributed according to the probabilities in the graph. What is the probabilities of a number being greater than 3.5? So we have this is actually kind of like a bar chart, but there's a probability here for 1, for the numbers in the range of 1, and I think the numbers should be, it should go like this: 1, 2, 3, 4, 5. I think that's how this should have been labeled. Okay, so the probability for between 1 and 2 is 30%. Probability between 2 and 3 is 20%. Between 3 and 4, that's 40%. And between 4 and 5, that's 10%. And you can see that if you add those all together, that's 100%. Okay, so the question here, what about probability greater than 3.5? So that's going to be halfway through the 3's. So we're going to find the area of the region that is bounded by that line, and then the rest, and it covers the rest of this bar chart. So we can think about that, that's kind of an L shape there. We can think about that as half of the 40% column, and notice that the widths are all 1, so this is half, the width is 1/2 and the length is 40%. And then this little tiny rectangle here has a width of 1 by a height of 10%. So 1/2 times 40% is 20%, plus 1 times 10% is 10%, and that equals 30%. So this region that's going to be defined as greater than 3.5 is 30% of the entire amount, and so that's the probability of getting a number greater than 3.5. Okay? So again, we're thinking of our probability distributions as areas instead of as discrete columns. Okay. I don't know if that made sense, but we'll keep going. All right, here we go. Here's another question. What is px greater than 5? This is some cool notation here. This is fancy mathematical notation. And what it means is P stands for probability. You probably guessed that. What's the probability that x, the variable, the horizontal variable x, is greater than 5? And so we find 5 here. And we draw a line going straight up. And then we're talking about the greater than side of that line. So the rest of the graph from 5 on over is going to be this triangle here. This triangle section, right? The entire probability distribution kind of looks like a trapezoid, but we're only trying to find out the probability defined by this triangle. So we're going to find the area of that triangle. And the area is 1/2 times the base, which is the number of spaces between 5 and 8. So we could count, it's 3, or we could just say 8 minus 5, which is 3. And then the height, and again on the chart, the height of that triangle is at the 20% line, so 0.2. So we multiply 1/2 times 3 times 0.2 is, and the answer that I'm getting doesn't sound right to me, so I'm gonna, oh yeah, it does. Okay, 0.3. We do it on the calculator, and we get 0.3, which is 30%. Okay, does that make sense to us? Looking at this, is this region here, is it reasonable to say that this region here is 1/3 of the total amount? And I think it's fairly reasonable. So yeah, we're going to say that looks right. Okay. When we're talking about kind of geometry, we're talking about areas, we always want to ask ourselves, does it make logical sense? Does it make sense that this is 1/3 of the total? And I think it does. Okay, let's do the second question here. Same format. What is P, this probability, of 2 less than x, which is less than 4? So this time we're asking, what's the probability that we're between 2 and 4? So this is a different region here. And we need to figure out how we're going to find the area of that region that's not, it's not actually a standard shape. It's a partial shape. There's a couple of ways we can think about this. We could cut it in half right down the middle. We could just draw this line here and find the area of the trapezoid on the left. The left half of that is a trapezoid, and then the area of the rectangle on the right, and we'd be good to go. I'm going to do it something different. See if you can follow this. I'll use the highlighter tool to try to highlight what I'm doing. I'm going to look at this entire rectangle here, and as I look at that rectangle, I notice, I notice that the rectangle is the area I'm looking for, except for this region right here. And that region matches up with this region right here, that triangle right there. So if I can just figure out the area of that triangle and subtract it from the area of the rectangle, I'll be good to go. So that's what that's the method I'm gonna do. You can do any method you like for calculating this area. So that's gonna be the rectangle is 2 spaces wide times the height is 0.2, and then we're going to subtract the area of the triangle, which is 1/2 times the base, which is the base is 1 space wide, and then the height. This one's a little bit harder to measure here, but I'm going to say that's point. I don't think. Well, I don't think it's. Is it halfway? Maybe it's halfway. So I'm going to say it's not quite halfway. So I'm going to say 0.7. I'm going to say that's, if we split that into 5, I'm going to say that's 0.7. Okay, so 0.07. Okay, so 2 times 0.2 is 0.4 minus half of 1 times 0.7 is 0.035. And so I subtract. Now, think about that. The number I'm subtracting is a really small number because it's just this little tiny triangle that we're subtracting from this relatively large rectangle. So it's just a small little sliver that we're cutting off. So 0.4 minus 0.035 is 0.365. So 36.5% is what that is percent, and there we have it. Now, I must say that that's probably the trickiest calculation of area that you're ever going to see, if even that. So don't get freaked out about this area stuff. Most of the time you're going to be finding areas of rectangles and triangles and maybe a trapezoid. Okay, let's do this. This is an actual quiz question. It's one of the trick questions. Question number 1. The graph shows the probability distribution which probabilities are equal to 25%. So what's tricky about this one is it gives you 4 different probabilities, and we have to figure out each one is that 25% or not. Okay, so we're just going to look at each one in turn. X is greater than or equal to 5. So from 5 up, is that 25%? Well, the height of that triangle is about halfway to 25%, so 12.5, 0.125, and the width is 1, so 1/2. The area of that triangle would be 1/2 times 1 times 0.125. So it's actually going to be half of 25%. So that's definitely not 25%. The area is not 25%. It's what is that? 6.25%. Okay, so no, the answer is no. How about the second one? 2 is less than or equal to x, which is less than or equal to 3. So that's talking about this square right here between 2 and 3, and the height is 25%. So that's a square or a rectangle. The base, the length is 1 between 2 and 3. 3 minus 2 is 1. So the width is 1, and the height is 25%. So 1 times 25%, of course, is 25%. So that one works. Okay, how about probability x is less than or equal to 2? Let me do a different color here. So this time we're taking the other side of 2, so 2 on down, that's this triangle right there. Now this is a triangle, so we're going to use the triangle formula. 1/2 times the base, which is, this time the base is 2 squares wide, so 1/2 times 2, times the height. This time the height is all the way up here at 25%, so 0.25. So 1/2 times 2, 1/2 times 2 is 1, half of 2 is 1. 1 times 25% is 25%, so that is, the area is 25%, so that one is also true. And then the last one, between x is greater than 3 and less than 4, so that's this region over here, which is also another square, just like The second one, it's a square with a width of 1 and the height of 25%, so the area is 25%. And so that one's true also. So this is an example of a question where you had 3 right answers and 1 wrong answer. And the question was asking for you to select all of the right answers, so that's pretty tricky, having to kind of make those determinations. All right, that's non-uniform probabilities, non-uniform, where the probability of 1 or between 1 and 2 was different than the probability of 3. The probability of 4 was different than the probability of 5 here. So the probabilities are not the same. So now we're going to just real quickly take a look at a couple of examples where we have a uniform probability. The probability of every item, not just the numbers, but the numbers between the numbers, is the same. And that puts us in this tricky little situation where since the probabilities are all the same, we can answer questions about the probabilities, the relative probabilities, without actually knowing what the number on the left is. What is the probability here? So I could put a question mark here and say I don't know what the probability for any one of these is, although actually we could figure it out really easily. I'll show you that in just a minute. So the number X of socks I lose each week in the dryer are distributed according to the probability distribution below. What is the probability to lose between 8 and 12 socks? Okay, so I actually made this question up, and now that I look at it, I realize, oops, this is not a continuous variable, because you can't lose half a sock in the dryer unless it's a really nasty dryer. So try to ignore that little mistake on my part. Let's go back to red so we can see. We're talking about between 8 and 12. So what's the probability of the number of socks that I lost being between those two numbers? The answer is we're trying to find the area of that rectangle. But really what we're trying to do is we're trying to find the probability of hitting in that rectangle out of the entire rectangle. So it turns out that we don't need to know the height. All we need to know is the widths. We need to know the width of the entire rectangle. So what's the width of the entire thing? And then what's the width of what we're trying to hit, what we're trying to get to between 8 and 12. And that's a probability. Remember, probability is just what we want divided by what could happen. I could hit anywhere in the blue rectangle. What I want to happen is to hit in the red rectangle. The width of the red rectangle is from 8 to 12, so 12 minus 8, which is 4. The width of the blue rectangle is from 3 to 13. 13 minus 3 is 10. So the probability is 4 to 10, 4 out of 10, which is 40%. Okay, why don't I need to know the height? Well, we could have done this with the probability of, let's just say I don't know what the height is, so I'm just going to say that h. So then the area of the red rectangle is 4 times h. The area of the blue rectangle is 10 times h. And so 4h divided by 10h, well, the h's cancel, and we're left with 4/10, which is 40%. So I didn't need to know the height in order to make this calculation of the probability, because this is a uniform probability all the way across. The height is the same for every part. I don't have to use that as part of my calculation. So that's handy. So that means that we can answer this question without knowing where this line is located. But let me just show you real quickly how we can find where the line's located. We said that the length of the blue rectangle is 10, 13 minus 3. So the total probability here from 3 to 13 is 10 wide. So remember the whole area, the area of a rectangle is length times width. The length is 10, and the area has to be 100% or 1. So the width then is going to be what times 10 equals 1. Divide by 10, the width equals 1/10, or 0.1, which is 10%. So we could have said this is 10%, and that is the height of the rectangle. But because of the nature of this uniform probability, it being a rectangle, we didn't even need to know that. All right, hope that wasn't too much information. Let's do this again real quickly on our last trick question. Graph shows the probability distribution. What is the probability between 1.5 and 3? So we'll get our pen here, and we'll draw a blue rectangle inside this pink one from 1.5 to 3. And again, we don't know what the height is. We could calculate it. The width of the pink rectangle is 1 to 4, so 4 minus 1 is 3. We can divide 1 by 3, and the probability is 1/3, or 33%. But we don't need to know that. But instead, all we need to know is the total width, which we just said is 3. 4 minus 1 is 3. And the width of the piece that we're trying to hit, and that's from 1.5 to 3, so 3 minus 1.5 is 1.5. The probability then is what we want in the 1.5 region divided by what could happen, the entire region, 3. And 1.5 divided by 3 ends up being 0.5 on your calculator. 1.5 is half of 3, which is 50%. So the region we're trying to get here is half of the total region, so the probability is 50%. All right, well, there you have it. Thank you very much for watching. I hope this helps you feel a little bit more comfortable with continuous random variables and the types of questions you'll see on the quiz. Make sure you give yourself an opportunity to go in and do the practice problems in the lesson before you jump into that quiz. Thanks for watching.